Welcome to today's Trane Engineers Newsletter Live program. I'm Jeanne Harshaw, and today we'll discuss retrofitting hydronic heating systems. We'll start our program by discussing electrification of heat and some challenges and benefits associated with it. Then we'll move on to lower fluid temperatures, coil requirements, and finding the right balance when retrofitting a hydronic system. Ronnie will then cover hydronic distribution and the zone heating and cooling units. And finally, we'll wrap up our program by discussing some steps for success. To cover today's topic, we have Trane application engineers Scott Delo and Sarah Hilden, and systems engineer Ronnie Moffitt. Scott, can you get our discussion started with potential challenges of electrifying HVAC systems?
Sure, Jeanne. With the industry and an increasing number of building owners looking to lower their carbon footprint, designers are being asked to electrify building heating systems. We've covered design trends on electrifying new buildings in previous E&Ls, but electrifying existing buildings presents several unique challenges that need to be addressed. The first and most common issue is that existing coils are selected for elevated hot water temperatures, often 180 degrees Fahrenheit. Radiant and convective units, whose capacity is closely tied to hot water supply temperature, may be difficult to address. Hot water distribution piping, sized for as high as 30-degree delta Ts, may limit hot water flow rates. As hot water supply temperatures drop, it may be necessary to increase the size of terminal units. The ceiling, plenum, or mechanical room dimensions may limit how large these components can get. Many existing buildings, particularly hospitals or large district or campus systems, still use steam heat that may need to be replaced. Steam is often used as a preheat coil since it's much less likely to freeze. When moving to hot water, the designer must consider freeze protection. And the last hurdle to electrifying heat, specifically in existing buildings, is cost. We'll discuss several options on how to address these issues. Before we get into the details, let's take a step back and review the benefits of electrifying heating systems. There are four key pillars that must be considered when designing sustainable building systems: energy efficiency, renewable energy, refrigerant management, and electrification of heat. Today we'll be focusing on electrification of heat. Let's briefly go over the benefits of electrification. The most obvious benefit of electrification is that it eliminates on-site carbon emissions. Depending on the electric grid and the efficiency of the electrified heating system, it may or may not reduce source emissions. Since electrified heating systems commonly have a coefficient of performance, or COP, significantly higher than that of fossil fuel-based systems, they also lower site energy consumption, or energy usage intensity. The last and often most important benefit is that properly designed systems may reduce operating costs. I'll turn it over to Sarah to go over electrified heating design considerations.
Often the first thing we get asked when an engineer is faced with an electrification project is, how hot can you make water with a heat pump or chiller? But we need to think more holistically. With reduced hot fluid temperature, coils may not have adequate transfer surface to make the original supplier temperature. When this is the case, action must be taken at the coil level. We can take the engineering approach. A typical coil selection program can provide data for changing conditions. By modifying fluid temperature into the coil, and for a given flow rate, we can see what happens to the approach on the air side. If pipes can support more flow, we may be able to send more water to the coil to maintain a given supplier temperature and volume. If not, there's more work to be done. At the zone level, based on a leaving air temperature, we need to know the volume of air required. If existing ductwork is being used, there may be a limit there. So the first question is, how much air and at what temperature is required to meet the design load? Once that has been determined, then we can begin to consider the coils. The coils themselves have minimum and maximum flow rates and velocity limits. So, if possible, modify coil inputs to identify those limits. Sometimes building owners will take a try and see approach. The systems may have already been oversized. On a cold day, reset the hot fluid temperature and then see where the cold calls come in. Those are coils that potentially need to be replaced or further investigation is warranted. In effort to retrofit existing buildings, there may be zone or system level equipment in play. To name a few, at the zone level, VAV boxes with reheat coils, fan coils, either changeover or 4-pipe units, may be in place. When it comes to air handling units, single or multiple zone VAV air handler unit coils are likely to require consideration, along with dedicated outdoor air units designed to condition 100% outdoor air that may have been receiving much warmer water in the past. As such, if equipment is aging out, a like-for-like drop-in may be inadequate, and some engineering time must be spent on a proper coil analysis using the new design conditions. Additionally, terminal units may have fewer coil geometry options and may influence the design hot fluid supply temperature more so than those inside the air handling units. On a positive note, many existing coils are already oversized. Why? Building envelope updates might have already reduced the heating load, and leakage rates may have improved from the original design, so less capacity is needed in the first place. It's also possible they were sized using rules of thumb from back in the day. On the flip side, changing occupancy rates might actually increase heating needs. Less people in the building, running lights and computers, takes from the internal loads that might otherwise offset the envelope load. A careful analysis of coils served can identify those inadequate at lower supply fluid temperatures. By starting at the zones, we can identify the minimum required fluid temperature. Then consider the increased airside pressure drop and the potential need for increased flow rates. There's a balance to be struck there. Increased piping diameter may be required to accommodate additional flow, impacting valves and pumps. As an example, for VAV reheat coils, additional rows may be required. Let's look at an example terminal unit. This diagram and table is from the engineer's newsletter, Heating with Lower Temperature Hot Water, which goes through trade-offs in more detail with real product data. One scenario, a single row coil selected for 180 degrees Fahrenheit with about a 50-degree delta T in the far left column, could be replaced by several different coils of the same capacity and still result in the same leaving air temperature and volume. The second to last column is a 3-row coil in a larger box, moving from an 8 to a 10-inch inlet damper diameter. For the same capacity, higher flow is required at similar air and water side pressure drops. If there's space, this might be a good trade-off for reducing hot fluid temperatures. This brings us to why reduced fluid temperature is beneficial. Shown in the graph are ASHRAE 90.1 minimum COPs for air-to-water heat pumps for heating. When looking at minimum efficiencies for the same equipment, delivering 105-degree Fahrenheit fluid is 35% more efficient than delivering 140-degree supply fluid. Simply put, the lower the fluid temperature delivered, the less energy consumed. As more buildings move to electric sources for heat, a larger percent of the overall grid demand will come from space heating. This is where designers have an opportunity to make a large impact. When retrofitting hydronic systems to electrify, early identification of limitations is critical and will help keep the project on schedule, within budget, and circumvent any impact on the occupied building. Keep in mind, the goal is to optimize system efficiency, not just the equipment selected. Later in the program, Ronnie will present example data that reinforces the need for analysis to make qualified decisions. In summary, it's certainly possible to retrofit existing hydronic heating systems to accommodate lower temperature heating fluid to maximize system efficiency through careful system design practices to enable efficient equipment operation. Reuse of coils is possible, even if flow rates increase, provided piping is adequate for increased flow rates for various terminal and air handling devices. Now let's discuss a few system options that are prevalent today. In general, we are seeing emergent system types frequently used in electrified systems, not only in retrofit scenarios. I will briefly discuss a few common system types and explain why certain options are selected over others. Sometimes, various systems are combined to maximize efficiency, minimize costs, and utilize available space. In a two-pipe changeover system, where the chillers are located outside, heat pumps are installed to perform double duty. Perhaps for a smaller school that has two-pipe hydronic distribution to local fan coils or unit vents. The system simply changes over based on outdoor air temperature, schedule, or even manually. With this type of system and a two-pipe heat pump and terminals, the changeover occurs at the unit. Prior to electrification, this may have been a chiller and a boiler piped and valved into a two-pipe distribution system. Here, an electrified system option is shown. The source of heat energy is from the ambient air. In this example, we have a packaged heat pump unit serving a two-pipe distribution system. The heat pump sees constant flow, and the pump likely requires two speed set points programmed into its VFD, as heating and cooling design flows may not be identical. The system is piped in a decoupled configuration with variable flow to the loads. Piping heat pumps in the primary-secondary configuration is common. It's simple, and operators understand it. This diagram illustrates a four-pipe variable flow distribution served by a packaged heat pump that can produce either hot or cold fluid. Again, the supply equipment sees constant flow, which may vary between heating and cooling, again in a decoupled arrangement. For a cooling dominant load profile, plant efficiency can be further improved with the inclusion of cooling-only chillers. Here, there are two. If gas is still not banned, some building owners are choosing to retain their existing boilers, but only using them as a backup option when the heat pump system is unable to meet the heating requirements due to cold weather conditions. In this scenario, when there are moderate loads and outdoor air temperature, the heat pump carries the heating load with boilers for fewer hours of the year. Selection of units is important as well. Try to match equipment to the loads to avoid oversizing in either heating or cooling when possible. Multiple units may be used for redundancy or turn-down capability. And don't forget to check the heating capacity at design heating conditions. It drops off with ambient temperature. In addition, a heat recovery chiller could be deployed between the distribution loops to further increase system efficiency. Notice, this unit is piped in the side stream position, drawing fluid off the return of both distribution streams. When it comes to heat recovery, there are several options available to explore. For a central plant, water-cooled machines will be used, so there is opportunity for heat recovery. A wise engineer once told me, the cheapest BTU is the one you already have. Consider including a heat recovery chiller to handle simultaneous loads for improved system efficiency. It is assumed that heat recovery requires a separate condenser, but when heating fluid temperature is reduced, many water-cooled chillers can also function as a heat recovery chiller. There are chillers with separate heat recovery bundles, split condenser bundles, or just a regular condenser. This table shows some trade-offs for each type of condenser. As an example, a second full-sized condenser can provide higher fluid temperatures than the smaller auxiliary condenser. That's why it's important to have as much understanding around what the load profile looks like and the required fluid temperature so the right piece of equipment can be selected. Depending on the coincident load magnitude, duration, and staging planned, these all provide options to reuse heat that would otherwise be rejected at varying levels of additional cost. The point is, if you're electrifying a heating system, reducing the load to be met with new equipment first provides operational savings to a building owner while also reducing their carbon footprint. Geothermal systems, when designed and operated properly, can be the most efficient system type, but they do require extra effort to ensure a solid design. These systems may be centralized with modest to large equipment in a plant. They may also be distributed with, as an example, relatively small local water source heat pump units connected to a building loop, which is in turn connected to a geothermal well field. In both cases, the geothermal field must be sized to sink and source energy to and from the earth. Identifying the peak and annual heating and cooling loads is important. Peak loads to ensure the geothermal field is adequate to source or sink the load needed. This may be important to ensure that the earth temperature does not rise or fall over time due to an annually unbalanced load. If this were to occur, system operation efficiency is degraded. For example, in a cooling dominant building, more heat is rejected to the earth than extracted. Eventually, the earth warms, resulting in elevated return fluid temperature. Increased fluid temperatures at the condensers of heat pumps in the building, whether distributed or central, bring increased energy consumption. The cooling units must produce more lift. Additionally, annual load profile analysis is required to determine whether supplemental heat adders or subtractors are required. We're seeing designers choose to apply air-to-water heat pumps to add or remove heat from the geothermal well field as an electrified option. Space and cost also come into play. Greenfield sites with ample space may be amenable to a geothermal well field if the funds are available. Let's look at one more option. Today's system designers have been applying thermal energy storage systems for heating as well. Some of this has been driven by federal tax incentives, specifically where the cost of geothermal wells or space constraints are prohibitive. In an existing 4-pipe distribution system, this can be an attractive retrofit option. One system option that was introduced in a prior Engineers Newsletter Live is the storage source heat pump system. This system allows for energy to be extracted from ice tanks when there's insufficient heat to be recovered, particularly during periods when the building requires heating. This decouples the heat source from being directly tied to outdoor air temperature, as would be the case in an air-to-water heat pump only system, enabling electrified heat even when it's cold outside. Storage source heat pump systems include a heating distribution loop, a cooling distribution loop, an air source and sink loop, and an energy transfer loop containing the thermal energy storage tanks. Air-to-water heat pump units source and sink energy from outside air to or from an energy transfer loop. They're also able to provide chilled water to the distribution loop. The water-to-water heat pump, which is a chiller controlled to a heating fluid set point, provides hot water to the heating distribution loop by extracting energy from the energy transfer loop, in turn freezing the tanks. The thermal energy storage tanks can collect energy from either the air-to-water heat pump, the building when we're cooling with ice, or both with their capacity controlled by the building automation system. The building automation system also coordinates airside economizer operation so as not to waste beneficial energy now if needed later. Operating modes from the distribution loop perspective include cooling only, heating only, and simultaneous heating and cooling. This system is flexible and offers an electrified heating solution even in cold climates. The options shared here are just a start. Engineers are becoming more innovative with hybrid approaches. These approaches may involve incorporating elements from the various systems discussed today to accommodate space limitations, balance costs, and adaptation to different supply and distribution piping configurations. The use of energy storage tanks in tandem with geothermal fields can reduce the wells required, and many of the other systems can benefit from the addition of an energy storage property to reduce equipment capacity. The inclusion of thermal storage in the system provides added flexibility, allowing for participation in demand response programs. The key takeaway is that there is no one-size-fits-all solution when it comes to retrofitting electrified heating systems. With that, I'll turn it over to Ronnie for more detail around distribution options.
Thank you, Sarah. So far, we have discussed retrofitting the central hydronic heating and cooling plant. However, this is only half the system. We are now going to look at the hydronic distribution and the zone heating and cooling units. The majority of the buildings that utilize hydronic heating and cooling systems are equipped with a 4-pipe distribution system. There is a central chase with very large pipes through the center of the building that distribute the water or glycol solution to and from the central plant. The 4 pipes are chilled water supply, chilled water return, and hot water supply and hot water return. The 4-pipe distribution system is not dependent on the type of heat pump equipment used in the central plant. For our example, the air-to-water heat pump is 2-pipe, but can be utilized in a 4-pipe distribution system. Piping branches off the central chase to areas of the building. This piping brings the heating and cooling fluid to and from the zones. Then zone piping runs to and from these branches, as required by the zone unit. Most existing zone fan coil units are also 4-pipe, containing a heating coil and cooling coil, and a fan to force air through the coils to exchange the heat either to or from the zone. And they have coils sized for 45-degree chilled water or colder, and small heating coils sized for 140-degree hot water or hotter. When retrofitting this system to use heat pumps for heating rather than a boiler, what changes? As it was mentioned, there is a significant heat pump efficiency gain when using a lower hot water supply temperature. When replacing the fan coils, the heating coils should not be sized for 140 degrees. Most fan coils, if selected and sized for it, can heat a building adequately with 105-degree hot water, and in some cases, as low as 95 degrees is possible. 105 instead of 140 can result in as much as a 45% improvement in heating efficiency. There are not too many opportunities where one can improve the efficiency of a process this much without changing to a higher cost piece of equipment. So what are the roadblocks that hinder the use of 105-degree hot water? Let's consider a worst-case scenario for forced flow heat exchangers, specifically the retrofitting of a space that has cabinet-style fan coils. Each dot in this chart represents a coil selection at various hot water supply temperatures. On the x-axis, the corresponding fluid temperature drop, delta T, is on the y-axis, with the average plotted along the dotted line. This is the expected range of fluid temperature drop when the coil is properly sized for the hot water supply temperature. In this example, the hot water supply is at a temperature of 140 degrees. The delta T of a coil size for this temperature is approximately 30 degrees. The delta T in a coil size for 105-degree supply is only 15 degrees. At this temperature, the coil will require twice the hot water flow at design. It's important to note this is the worst case equipment, since it's typically the most space constraint. For example, coils in the central air handlers can be designed for 30-degree delta T with 105-degree hot water. For our fan coil example, one may be thinking with twice the flow, won't the pumping power double? Won't that wipe out energy savings of using the lower supply temperature? The answer is no, not even close. We will go over that in a minute. Let's look at an example replacement scenario for this type of fan coil. The existing equipment has a 2-row preheat coil using 140 degrees hot water and a 2-row cooling coil using 44-degree chilled water. The delta T for heating is 33 degrees and for cooling it is 10 degrees. The replacement fan coil has a single 4-row dual-purpose coil. It is designed for the same heating capacity using 105-degree glycol with a 15-degree delta T. For cooling, it uses the same 4-row coil to achieve the same cooling capacity It needs 1/3 less flow and has an 18-degree delta T. Extra airflow is not needed to meet heating capacity. The previous 95-degree design heating leaving air temperature is achieved with 105-degree hot water. It is important that the replacement unit does not take up any additional space due to the value of finished space in a commercial building. There is no extra room for 8 rows of coil, so we must stick with 4 rows. Because both the hot water and chilled water supply come from the same central equipment, the same coil can be used for both heating and cooling. But how is this achieved? How do we switch the fluid temperature provided to the fan coil from heating to cooling and vice versa? One available option is a 6-way control valve. This will allow for the coil to be used for either heating and cooling. However, this requires significant space to accommodate both the piping and the valve. It also adds additional cost to the retrofit. One 6-way valve is more expensive than 2 2-way valves and zone controls. Plus, it's more complex. If one can find space to incorporate the 6-way control valve option, there's another issue that arises: the distribution piping. Changing from 140-degree supply hot water to 105 degrees requires 2.5 times more in our example system. That means new branch and zone hot water piping will be required to make this option work. In retrofit scenarios, there is an alternative solution that may be applicable in some cases. To illustrate, let's consider a common architectural design known as a finger school, characterized by classroom wings branching off from the center of the building. This building has existing 4-pipe distribution with fan coils or unit ventilators in each classroom. At the center of the building, there is a central chase with large distribution piping. Each classroom wing has 2 sets of branch piping for each facade. This is sized for 44-degree chilled water and 140-degree hot water. Each branch then feeds 8 to 10 zones with 4 pipe connections to the fan coils or unit vents. The problem with using 6-way valves at each zone is that the existing hot water branch piping is sized for 30-degree delta T and is not able to handle the added flow required for the same heating capacity. The existing 3/4 inch diameter hot water zone piping needs to be retrofitted to 1 inch for the 105-degree supply water to match heating capacity. And the existing 1.5 inch branch piping now needs to be 2 inches to match the heating capacity. The dual-purpose coil will allow for larger cooling delta T. The existing piping will be able to deliver additional cooling capacity. Replacing this branch and zone piping with larger sizes is costly and requires construction work in the occupied space of the building, which many owners wish to avoid. Is there a way to minimize this without having to go back to 140-degree supply water? 4-pipe distribution is desirable because it allows some zones to provide heating while others provide cooling. But simultaneous need for heating and cooling is rare in this type of building, and when needed, it is usually in the non-adjacent areas of the building. In the shoulder months, there may be early morning or late afternoon solar loads that require cooling in some of the areas, while heating is needed in others. This can be true if there's a dedicated outdoor air system serving fan coil units that do not economize. In our example school building, the classroom wings can be divided into 8 thermal areas. Throughout most of the year, these thermal areas will require either cooling or heating, but for those few early morning fall or spring sunny days, some of these thermal areas require cooling, while the rest need heating. Instead of resizing the existing branch hot water piping to match the new flows required, there's already piping that matches the needs. That is the cooling piping. The branch cooling piping can also be used for heating. When replacing the existing units, the new terminal units will be equipped with only one dual-purpose coil that will switch over between cooling and heating. The 1-inch zone chilled water piping is large enough for heating also, so the zone hot water piping and the second heating control valve are no longer necessary. This 2-inch branch chilled water piping is already correctly sized for heating also. So this branch hot water piping is no longer needed. It can be disconnected, drained, capped, and left in place to prevent disruption to the finished space. Or it can be reused if there is heating-only equipment installed. With the new terminal units, switchover occurs at the branch connection for each thermal area. This switch to heating from cooling or from cooling to heating is accomplished by a distribution area director, or DAD. This valve control unit directs either heating or cooling fluid to and from the area based on the current need, and there's no additional piping or valves required in the zone. Each zone-level terminal unit is controlled with a traditional two-way modulating valve, but now it has only one valve per zone. It is important to note the DAD does not control the zones. Each zone still has independent control. As shown in this example, the thermal areas can be in different modes. The left-hand area is in cooling mode, so the DAD directs chilled water to the coils in these zones, while the right-hand area is in the heating mode, so the DAD directs hot water to these zones. So this approach is able to provide simultaneous heating and cooling in different areas of the building if needed. Each fan coil unit communicates its current mode to the building automation system. The BAS then determines if heating or cooling is required for that area and instructs the DAD to redirect the appropriate fluid. Let's revisit our example school. During the shoulder months, the heating and cooling demands may vary depending on the zone. The south side of the school may require cooling, while the north side may require heating. The fan coils serving the south wing are all call for cooling, so the DAD sends chilled water to the zones in that area. For the north side, all but one zone are calling for heating, so the DAD sends hot water to these zones. The distribution area director sends the fluid needed for the thermal area, but it does not control the area. The zone-level units still control as they do in the current 4-pipe system, with independent modes and independent valve control, as needed to satisfy the zone set points. The DAD just delivers heating or cooling fluid based on the current requirements of the thermal area, and may only switch over periodically throughout the year. Zones can be in heat mode when the area is in cool, or zones can be in cool mode when the area is in heat. Each zone has a temperature sensor to determine if hot or cold water is being currently supplied to the zone, so the zone level controller does not need to communicate with the BAS or the DAD to control. If a zone calls for cooling, but only hot water is currently being provided by the DAD, as in this example, the fan coil controller will not open the valve. This prevents zones from fighting. This zone could cool with outdoor air by economizing. Or if this is a dedicated outdoor air system, the conditioned ventilation air could cool the zone. It may take longer to get to set point, but this will minimize the adjacent zones from fighting. The same will occur in cooling season. If one rogue zone calls for heating when it's hot outside, and the thermal area is in cooling, the unit will sense cold water and not open the valve. The space load will cause the temperature to rise in the zone. It'll just take a little longer and prevent zones from fighting and wasting energy. Let's pause here and talk about pumping energy use. Recall the existing system was sized for 10-degree delta T in cooling. The 15-degree delta T in the new design will reduce chilled water flow by 33% and reduce cooling pump energy further by reusing what is now oversized branch and zone piping. However, the new design has a 15-degree delta T in heating, which doubles the zone hot water flow rate. In the big picture, the increase in distribution pumping power for heating is small compared to the heat pump power savings due to using 105-degree hot water, although the same is not true for cooling. To demonstrate this, this bar graph represents cooling design day with 1 million BTU per hour of cooling load. Changing from a 10-degree delta T to 15 degrees saves significant pumping power. This does require lowering the chilled water supply temperature to 42 degrees, but the additional compressor power is smaller than the pump power savings, resulting in overall savings. How about heating operation with a 1,000,000 BTU per hour heating load? The left red bar shows the air-to-water heat pump operating at a 10-degree ambient temperature and supplying 130-degree water to the fan coils. The right red bar shows a large power reduction when the heat pump supplies 105-degree water. As shown in gray, there is a significant increase in pump power with a 105-degree supply and a 15-degree delta T. But the combined heat pump plus pumping power is still 30% less than the system designed for a 130-degree supply and a 30-degree delta T. That's an additional 54 kilowatts for a 1,000,000 BTU per hour. At part load, these savings continue. The far right bars depict 25% of the design heating load at 35-degree ambient. Overall, for fan coil systems, if you're constrained to reuse existing hot water piping in a 30-degree delta T, this will result in 30 to 45% more power to deliver the heat to the zones. So there is a substantial energy and power benefit of using area switchover in coils that are sized for both heating and cooling. Let's look at another scenario. This building has a two-pipe system for hydronic cooling with electric heat in each zone terminal unit. The new terminal units are equipped with a single hydronic coil and control valve. Area switchover is provided by adding the distribution area directors. The only additional requirement would be to install centralized hot water piping in the building. This change to hydronic heat pump heating should be a huge energy and cost savings. Referring back to the finger school example, using a distribution area director for the classroom wings removes the need to add more than 2,600 feet of branch piping and 1,200 feet of zone piping, 60 zone coil connections, and 60 six-way valves. The central piping will need to be updated to add hot water supply and return piping in just the central chase, and a distribution area director will be added for each of the 8 thermal areas. Note, the remaining portion of the school building will have traditional 4-pipe air handlers serving the gym, cafeteria, and other zones. Distribution area directors may be used in some areas, however, it is not used for every zone in a building. Let's look at another common existing system, that being a water source heat pump system. What options are available to electrify this system in an existing building? One option is to replace the gas boiler with a heat pump to inject heat into the loop during cold weather. This offers the added benefit providing some extra cooling capacity during warm weather. If the existing system uses a packaged DX dedicated outdoor air unit, you might add a chilled water air handler or terminal units to utilize this excess cooling capacity. But a DX unit often uses either gas or electric heat, so you would add a new hydronic dedicated outdoor air handler for ventilation. This can be used in the winter months also. The air-to-water heat pump sends hot water to the air handler to warm the outdoor air from 0 degrees to 75 degrees. And a hydronic air handler is very capable of very low turndown of airflow for demand control ventilation. Using an air-to-water heat pump with a hydronic outdoor air handler enables these energy savings that may not be possible with a DX dedicated outdoor air unit. Water source heat pump systems can be electrified without major changes to the system. But in some cases, the school district or a building owner may want to replace parts of the system to eliminate compressors near the occupied space or to eliminate cooling towers. In this type of system, the existing distribution piping is typically large, designed for a 9-degree delta T. The distribution area director concept can successfully reuse the piping to supply either chilled water or hot water to the new closet air handlers instead of the heat pumps. In this case, each heat pump is replaced with a similar sized vertical air handler. A distribution area director is added that enables switchover for each area, reusing the distribution piping. Central hot water supply and return piping will need to be added to the building for this retrofit option to work. For this example, the dual-purpose coil in the vertical air handler is sized for 21 degree delta T in both cooling and heating. In heating, it can warm air from 55 to 95 degrees using 105 degree hot water. In conclusion, if the zone conditioning units are being replaced, size the zone units for the lowest hot water supply temperature that can meet the space load. Use the same coil for both heating and cooling where possible, and make use of thermal area switchover with distribution area directors to simplify branch and zone piping and control. I will now turn it over to Scott to cover some common design issues.
Thanks, Ronnie. Buildings with process loads, radiant systems, or terminal units that weren't upgraded often require much higher hot water supply temperatures. One of the common issues that designers run into when designing an electrified heating system is that the air-to-water heat pump or water-to-water heat pump can't make the required hot water supply temperature. So what options do you have? First, implementing a hot water supply reset, often based on outdoor conditions, limits the number of hours when higher hot water supply temperatures are required. Second, supplemental electric or fossil fuel boilers may be used to reach higher hot water supply temperatures. In many cases, the building might have an existing boiler that could be used for this purpose at no additional first cost to the building owner. The downside is that these units have low efficiencies and potentially high carbon emissions. A third option would be to add another unit in a booster arrangement to reach the required hot water supply temperature. Cascade or booster systems add a second unit to boost the hot water supply temperature to temperatures not attainable with only one unit. In this case, an air-to-water heat pump operating and heating at cold ambient conditions may only be able to provide 90 to 100 degrees Fahrenheit hot water supply temperature. Instead of sending that warm hot water to the building terminal units, it's sent to a booster heat pump evaporator, creating an intermediate loop. The booster condenser can then be piped to the building terminals and supply hot water temperatures of 160 or even as high as 200 degrees, depending on the unit. The downside to these systems is that adding another unit will increase system cost and may decrease efficiency. This is not a replacement for designing systems to lower hot water supply temperatures, but may be useful in certain retrofit situations. This concept may be used to boost temperatures in various plant layouts and situations. Let's look at how this might be piped in an air-to-water heat pump system. Here we have a traditional air-to-water heat pump system piped in a dual decoupled arrangement. As mentioned earlier, the limitation is that hot water supply temperatures are dependent on ambient conditions and may not be suitable for some retrofit situations. Instead of sending the warm supply to the building, a booster heat pump can be added between the air-to-water heat pump and the building hot water distribution to achieve much higher hot water supply temperatures. Since the air-to-water heat pump is controlled to a lower hot water supply temperature, 75 degrees Fahrenheit for instance, the air-to-water heat pump capacity and efficiency is improved. To keep the control simple, and since the flow rates are often selected near the unit minimum, both the evaporator and condenser side of the booster are piped in primary-secondary arrangement. But what if we have existing coils selected for higher temperatures and new coils selected at lower hot water supply temperatures? In cases where a new renovation or addition must be tied into the existing building hot water heating system, but it's designed for lower heating temperatures, a second piping loop with a mixing valve can be added to the system to achieve both hot water supply temperatures. Designing the additional loop and mixing valve, instead of having the air-to-water heat pump satisfy the lower heating hot water temperature, sacrifices some efficiency, but significantly reduces control complexity and may improve the air-to-water heat pump capacity, lowering system first costs. Now that we've covered how to achieve higher heating temperatures, I'll turn it back over to Ronnie.
Let's look at retrofitting another common system type, the multiple zone VAV system. When retrofitting this type of system, the existing VAV boxes usually contain either an electric heater or hydronic coil with a hot water supply of 180 degrees or 140 degrees. These systems commonly have a heating supply air temperature of 95 degrees or higher. Today's heating design standards prescribe a lower supply air temperature when heating to reduce energy use. This is unrelated to heat pumps. In most VAV systems, heated air is supplied through ceiling diffusers. If supply air temperature is above 85 degrees, this will reduce the effectiveness of delivering ventilation to the breathing zone and will require 20% more outdoor air to the zone. Increasing the ventilation requirement in winter by 20% is a big energy increase if the zone is not already overventilated. ASHRAE 90.1 also prescribes supply air temperature not to be above 90 degrees when delivered from ceiling to effectively deliver the heat to the zone. A heating supply air temperature in the 80s in most cases will require 105 degree water with 4-row heating coils in the VAV boxes. Here's what zone heating with 105 degree water looks like. During stage 1 of heating, the hot water valve modulates to maintain zone temperature at set point, with the air valve at minimum airflow. During stage 1, the water delta T is 20 to 30 degrees. For most buildings, the majority of heating hours are in this stage. If the heating load increases in stage 2 of the heating, the hot water valve modulates to maintain the supply air temperature at a set point of 85 degrees, for example, while the air valve opens further, modulating to maintain zone temperature at set point. During stage 2, the water delta T is 12 to 18 degrees. I show this graph to highlight what Sarah said earlier about requiring decoupled systems. Most heat pumps like a delta T less than 12 degrees at the condenser. However, the VAV boxes are 12 to 30 degree delta T, so a decoupled distribution system is needed for the VAV and fan coil systems that were discussed earlier. The idea of heating with 105 degree hot water and 85 degree air can be received with skepticism, as this is different from existing systems being retrofitted. So let's review some case study data where an existing VAV system with 180 degree hot water was replaced with a VAV system using 105 degree water and 4-row heating coils. This is a 2-story building located in a cold climate, La Crosse, Wisconsin. The existing air handlers were reused, but the occupied spaces were renovated with new ductwork, VAV boxes, and hot water piping installed. This is a 2nd-story floor plan. It's served by 3 different multiple zone VAV systems, reusing the 3 existing air handlers. I'll focus on the 8,000 CFM VAV system that serves the north part of the building, shaded in purple. It conditions the lecture hall and student lounge, both with perimeter glass. To demonstrate the VAV box control performance, let's look specifically at this corner zone on the student lounge. It's 832 square feet and conditioned with a VAV box with 2140 CFM design airflow and a 4-row coil selected for an 85 degree heating supply air temperature. This chart demonstrates how the box successfully conditioned the zone on an 8 degree winter day. During unoccupied hours, the temperature in the space was allowed to drift to 65 degrees. But then the predictive morning warm-up starts, and the air valve and hot water valve are fully open. This raises the room temperature from 65 degrees to 70 degrees. The occupied period of the day then starts with the VAV box at stage 1 heat, air valve at minimum flow, and the valve modulating. During the coldest part of the day, stage 2 heat is needed. Airflow varies between 30 and 78%, with the water valve controlling to 85 degrees supplier temperature. Later in the day, back down to stage 1 heat, with the air valve at minimum and the supplier temperature varying between 60 and 85 degrees. So on this very cold day, even when nighttime unoccupied setback was used, the room was heated as designed using only 105-degree hot water. There is also hesitancy to use a 4-row coil in a VAV box because of the extra pressure drop. One could always upsize the box and coil to reduce this pressure drop, but for this case study project, the VAV box was not oversized, and the coil pressure drop is 0.64 inches at design flow. This may seem high, but the unit does not operate at high airflows all the time. Here is the full year recorded airflows delivered to this zone, measured every 15 minutes. This VAV box was observed to run at 30% minimum airflow for 39% of the year, which is over half of the total operating hours. So you can see this box does not run at high airflows often, since supplying 85-degree air does not require a lot of airflow to meet the heat load. There will be more fan energy, however it will be small compared to using the alternative of hotter water. For this VAV system, when supplying 100% design airflow during morning warm-up, the VAV box with a 4-row coil adds 0.5 kilowatts to the fan power. But if 2-row coils were used, 135-degree hot water would be needed. Operating the water-to-water heat pump at 105 degrees rather than 135 degrees reduces the heat pump power by 8 kilowatts. So 105 degrees and 4-row coils save 16 times more heat pump power than it adds in fan power. In summary, multiple zone VAV systems are a very good system to electrify. It will take new VAV boxes and new hot water piping to get the most efficiency out of the heat pump plant. If you don't do this and attempt to reuse 1-row coils, you may need to use the method Scott just reviewed to boost the water temperature to 165. How to decide what gets retrofitted and with what should be reviewed with the goals of the project. We should not lose sight of what the goal of the specific project is. Sarah, help us out here.
Wow, Ronnie, the wheels are really turning now. Thanks for that. Let's move on to planning and execution and what goes into it. The most important part of any project is making sure the entire team understands the project goals. Understanding not only the building owner or client's goals, but also any apprehension or concerns that the project team has up front results in a smoother project. For large buildings and campuses, the first step is often to establish design standards that align with decarbonization or electrification goals, if that's important to the owner. These standards should, at a minimum, establish design criteria for lower temperature hot water coils and prevent new steam or high temperature hot water coils from being installed in new buildings and discourage them in existing building renovations. Once the project goals are clearly understood and documented amongst all members of the team, the next step is usually survey work. During the building survey, it's critical that all hot water heating, domestic hot water, and steam uses are identified. Coil capacities and physical dimensions, including face area, design airflow, tube rows, and fin spacing, are important for future analysis. Pay particular attention to perimeter baseboard, radiant systems, and any process loads since they're often the most difficult to convert to lower temperatures. When steam preheat coils are used in cold climates, it is important to consider glycol or other methods of freeze protection when converting to hot water, especially in units with high outside air percentages. Depending on the facility, having a dedicated preheat hot fluid loop with glycol may be beneficial. Now let's take a moment to discuss loads. Having a good understanding of your system loads allows for better decision-making when it comes to selecting the type and size of equipment. Oversized equipment not only increases costs, but may create operational issues like excessive cycling and temperature fluctuations. Shown here are the cooling and heating load profiles for a hospital. When we rearrange that data, we better understand the impact of loads on unit sizing. This data is linked to the project goals. Many buildings require cooling year-round. Interior building zones don't lose heat through their envelope, but they still have interior loads to cool even when it's cold outside. Reheat for multiple zone VAV systems, tempering supply air for off-design zones, or dehumidification in humid hours represent typical coincident loads. Knowing the maximum coincident load informs the necessary capacity for heat recovery. Don't buy more than is required. Peak loads determine equipment capacity required for heating and cooling. When decarbonization is important, there are varying degrees to which it might be taken. If the intent is to recover heat, we want units with capacity near or below the peak simultaneous heating and cooling loads. Ideally, the equipment captures a base load, recovering heat all or most of the time. Anything beyond this leads to higher installation costs and increased operational hours with little or no load. If the goal is full heating electrification, then the units must be sized to satisfy the peak heat load. But maybe in some areas, it's okay to handle most of the heat load with a smaller boiler acting as a peaker unit like we saw earlier. This may provide more heating options: electric or fossil fuel boilers, heat pump water heaters, renewable natural gas, to name a few, satisfying those extreme loads. Many projects, especially in cold climates, are successful since peak heating days can be infrequent, resulting in significant electrification. Additionally, in systems with centrifugal heating chillers, it may be necessary to keep a unit loaded to avoid entering the surge region. This results in a unit capacity similar to that for the heat recovery goal. Now let's discuss central plant capacity. Designers may opt to simply replace existing heating equipment with electric equipment of the same capacity. However, we discourage this practice without further analysis. Heating systems are often oversized, even excessively so. Because electrified heating equipment commands a higher price tag, it may be worth the time and money to conduct a more detailed analysis. This might mean gathering trend data during winter conditions, if possible within the project timeline. If the data exists already, even better. If that's not possible, a detailed energy model is a good substitute, accounting for actual ambient conditions and building operating schedules. The designer must carefully balance risk management without oversizing the central plant. In many cases, this results in more pieces of smaller equipment. Of particular interest are heat pump plants serving double duty. For example, in cooling dominant climates, equipment sized for cooling will cycle in heating mode. Another facet in these projects is to determine how low the fluid temperature can be reduced. I'll turn it back to Scott for more on this.
Thanks, Sarah. Once all the building survey work is complete and the load profile is known, the analysis can begin to determine the optimal hot water supply temperature. As Sarah went over a few minutes ago, lower hot water supply temperatures improve unit capacity, efficiency, and selection options. The lower the hot water supply temperature, the better. With that in mind, one method to determine the optimal hot water temperature is to test the building systems. Lower the hot water supply temperature and identify the temperature where coils start to lose discharge air or space temperature control. It's common for systems designed for 180 degrees Fahrenheit to function with 160 or in some cases hot water supply temperatures in the 140s. If the domestic hot water system is tied into the building heating hot water system, it's often best to separate it. This allows the building hot water supply temperature to drop below that required by the domestic hot water system. Remember that not every coil in the system needs to be replaced, in order to supply the building with lower hot water temperatures, identifying and selectively replacing only the coils that failed to provide sufficient heating capacity during testing or modeling helps keep the project scope and therefore cost at a more manageable level. Once the capacity, supply temperatures, and flow rates of the central plant are determined, the last piece of the puzzle is what will the building heat source be? We've seen a lot of creativity in selecting heat sources to meet building heating needs. We talked about heat recovery being step 0. But in terms of keeping a more constant source temperature, the mass of the Earth and its bodies of water can be stable sources. Designers are becoming more creative and using other waste heat sources from the building, which is just another form of heat recovery, using wastewater or air leaving the building. And finally, thermal energy storage can provide a relatively compact energy storage from which to draw from where space is limited. Now that the central plant loads, temperatures, and heat sources are known, a central plant system type can be selected and design can begin. Since each project may require a unique solution, I won't go over any specific plant designs today. Previous ENL programs and application guides and manuals have covered several electrified solutions, including dual decoupled air-to-water heat pumps, central geothermal, and storage source heat pump systems. Last, cost is always important to a building owner, regardless of other competing goals. Certain systems, like geothermal and thermal storage, qualify for federal incentives, and many owners are leveraging those funds to get projects kicked off. Even with sustainability goals driving development, payback and first cost often drive project outcomes. When value engineering comes up, the designer must remember what the original project goals were and ensure that they are not lost in the value engineering process. Life cycle analysis demonstrating operational savings may be one way to overcome objections to first costs in retrofit projects. It's also worth considering helping a building owner think about future investments. Other smaller projects, including optimizing control strategies throughout the building, can help offset some costs. In conclusion, retrofitting hydronic heating systems help owners meet their decarbonization goals. Lower hot water supply temperatures are possible in existing buildings and improve system efficiency, capacity, and provide more unit options that may lower project costs. For buildings with terminal units that may not be capable of large cooling and heating coils, consider using adaptive or changeover coils with 4-pipe distribution using a distribution area director. As Ronnie showed, it can significantly lower project first cost. Where higher heating supply temperatures are necessary, use booster chillers to achieve the required hot water supply temperature. As always, remember that the simpler solution is often best, and operator education on plant operation is key to long-term efficient operation of the building. And now I'll turn it back over to Jeanne to wrap up the program.
So that is our overview of retrofitting hydronic heating systems. We hope you found it a helpful way to learn about this subject. Please fill out a survey to let us know what you thought of today's program. And as always, the bibliography included with the handout provides more information on where to find a number of resources related to today's topic, including the engineer's newsletter. Or contact your local Trane account manager for specific information on Trane systems, equipment, controls, and services. For those of you seeking continuing education credit, check out the newest online courses at the Trane Education Center, all free and available 24/7. And finally, for those of you viewing in person, please ask your local host about details for the upcoming Engineers Newsletter Live programs. The yearly program lineup can also be located at www.trane.com/ENL. Thanks for joining us today. We look forward to seeing you next time.